Okay, great, everyone. Hi, my name is Randy Shu, and I have the privilege today of hosting Dr. Neil Thompson for a paper talk on a very crucial topic, essentially of AI's impact on the labor market and how it potentially will displace or automate certain types of work. So Dr. Neil Thompson is the director of the Future Tech Research Project at MIT's CSAIL, Computer Science and Artificial Intelligence Lab. He's also a principal investigator at MIT's Initiative on the Digital Economy, IDE, where we have a number of Luohan friends, such as Jeff Parker, Marshall Van Alsten, David Otter. Now, previously, he was an assistant professor of innovation strategy at the Sloan School of Management at MIT, and he co-directed the Experimental Innovation Lab there. I believe you overlapped with our other Luohan friend, Brian Wolfson, now at Stanford. Dr. Thompson has advised businesses and governments on technology strategy as well as competitiveness. And if he seems like he has a very multifaceted background, it probably started with his multifaceted academic background. He has PhD in business and public policy, but also degrees in computer science and statistics. So, as I mentioned, the impact of AI on the labor market is one of the most crucial issues being discussed around the world, with profound implications for society and for our economies. A number of Luohan scholars have opined on this issue and are doing work in this issue, such as Michael Spence, David Otter, Chris Pisarides, Anton Kornek, Joshua Gans, Avi Goldfarb. We've actually hosted to talk about the impact of AI. So we're glad to have any research that advances our knowledge here. So with that, without further ado, I'll hand it off to Dr. Neil Thompson for his talk on his recent paper, Beyond AI Exposure, which tasks are cost-effective to automate with computer vision.
Wonderful. Thank you very much, Randy. Okay, so I want to, as Randy was already saying, I'm quite excited today to tell you about some work that we've been doing looking at job automation with AI. And I just want to acknowledge my co-authors here, both from MIT and the Productivity Institute and IBM. This is some work that was done jointly as part of the MIT IBM AI lab that we have here at MIT. Okay, so I want to start out by just saying, why is it so important to ask this question, not only about whether AI could do things, but actually whether it's cost effective to do things. And that's because the scale of disruption that we're going to get in society, both on the good in terms of productivity gains and on the bad in terms of people losing their jobs, really, really depends on the pace that this actually happens at. And some predictions about pace are incredibly rapid. So, for example, in the recent Harvard Business School review, HBR review, they're saying, "Oh, is AI coming for your job?" And quantitatively, PricewaterhouseCoopers released an announcement that said that 50 million Americans will lose their job by 2030. The Bank of England released a paper saying that 80 million jobs would be replaced by 2035. Now, these are US jobs, but if you think about, the US workforce is about 165 million. So this is saying, the Bank of England is saying like half of all US employees would lose their job between now and 2035, right? This would be an enormous disruption in the economy. Okay, so, this is clearly like, it's either like an incredibly important policy question, right? Or there's something else going on here that would make us moderated or think differently about the policy implications. All right, so this is really important more generally as well, because at the policy level, there's this big question about what AI job replacement is going to do, right? So I think economists often default to the farm automation analogy, right? So we say, well, look, an enormous fraction of the workforce used to be in agriculture. They moved to, as agriculture got automated, they moved to manufacturing. And what happened in those times is that there were some transitional costs, right? There were still some people who retired early or became more impoverished because of this. But overall, labor was able to adjust. it was not terrible for society. We got the productivity benefits without having a huge, like, persistent unemployment problem. And of course, if that's the answer, that's pretty good, because we're going to get a lot of the productivity benefits. The worrisome version of this is mass unemployment, right? So I think if you talk to a lot of computer scientists, they'll say, well, automation is happening faster and faster. And that means that you could easily imagine a world where you lose your job and you start retraining. But in fact, by the time you've retrained for the next job, automation has come for that job as well, right? And under that world, we end up with mass unemployment because people cannot adjust fast enough, and you end up with real systemic problems that could be worrisome. Okay, so with these two concepts in mind, we want to think about the broad question that we're going to talk about today, which is, what share of tasks is it economically attractive to replace human workers with? And here we're going to talk specifically about computer vision AI systems. Okay, now, obviously a lot of attention right now about large language models. I'll come back to that in a second, but we're going to focus on computer vision because there's actually a lot of historical data and a lot of work that has been done on the cost effectiveness, including by us, to be able to figure out the answer to this question. And then, of course, what we want to know is both what's going to happen, what's attractive now, but also how this is going to change over time. And then lastly, as I just mentioned, we're interested in how these changes are going to apply more broadly to other types of AI automation, right? And so if you are worried about large language models particularly, we'll actually have some things to say about that based on the economics we discover here. Okay. All right. So in the stuff that is going to follow, I do want to make one important caveat, and that is about what we are modeling and what we aren't modeling. So what we are modeling is substitution, the taking stuff that a human is doing and replacing that with an AI system, right? And the reason I say that substitution matters is two things. So one is, there's a lot of talk about, well, a particular job might be at risk of AI automation, or excuse me, at risk of AI exposure, but that might mean you just become more productive. Like, it's going to be an augmentation thing. That, of course, is pretty good, right? If the worker gets more productive and doesn't lose their job, that's a pretty good outcome. We're not really worried about that here. So the first thing is we're thinking about the replacement side, the actual automation side of it. But the second thing here is that we're when we focus on the human functionality, what we're thinking about is what's sometimes called Turing trap job automation, which is the human did it, now the machine is going to do it. What we aren't going to talk about is our new capabilities and new processes, right? And we know that in the long term, this is going to matter a lot, but it's not something that is very easy to explore, right? And so you can have in your mind here the transition to electricity, where we saw that initially, there was a replacement, but factory designs, for example, were not changed. And then over time, people realized you could adjust your process more such that you could get even more benefits. Of course, we still expect that to be true here. We just, there's not a really good way of saying, well, what is the labor division going to look like under those circumstances? And so that is going to sit in the background. It's a limitation of what we, and I think others, can do as well. But I just wanted to highlight that here because we do expect that process to roll out, but it will just be a longer process that will take time. Okay, so with all that said, let me talk about the agenda and what I'm going to talk you through today. So the first thing I want to do is I want to build up a framework for how you can assess AI cost effectiveness, which is going to be really at the heart of our paper. Then we're going to estimate the share of task replacement that is economically attractive in the US economy. And then we're going to do some simulations and say, well, if we think about AI usage spreading through the economy, right, you've got there's some fraction of jobs that are going to be attractive today, but then there's going to be a process that extends out. And we're going to think about this in terms of AI platforms that could emerge or cost improvements that can happen. And then lastly, we'll extend this and think about how this framework is also going to apply to large language models and the world of generative AI, which of course is very hot at the moment. Okay, so let's think first of all, in terms of building this cost effectiveness framework, about AI exposure, the measure that has been traditionally used, and what that would mean for a vision system. And so in particular, we want to ask, could an AI vision system do this task? So this is sort of a technically, could you imagine it doing that? And so like others, we're going to start here with the Bureau of Labor Statistics ONET database. There's a big database of different jobs and different tasks. And you can see here we have bakers. And if you look at the tasks that bakers have, you can see that there's one that says check products for quality and identify damaged or expired goods, mix dough according to a recipe, and then a whole bunch more. And you can ask yourself, well, okay, if I imagine a computer vision system out there in the world, and I said, well, could this computer vision system actually do each of these individual tasks? Well, you say, well, mix dough according to a recipe, surely not, right? That mixing is a very physical process. You need a human or you need a robot or something like that. That can't be done just with a vision system. But checking products for quality and identifying damaged goods, actually, you could imagine that, right? You could imagine a bakery that puts some cameras in the ceiling and then it highlights and says, don't use this batch. Some of the, bananas have gone bad or something like that. And the vision system could be detecting that. Okay, so if you do an AI exposure analysis, right, you would say, okay, this task is at risk of AI and this one is not at risk. And you would get to this answer, which often can actually be very substantial, like the assumption, the analysis that people have done on this. For example, there's a paper called GPTs are GPTs, and that predicted that about 50% of tasks could be automated with large language models. But there's an important caveat. And that important caveat is cost effectiveness. So let's actually think about automating this in a bakery. Okay, well, if you actually sort of infer from the data that the Bureau of Labor Statistics has, about 6% of a baker's job is to check products for quality and identify damaged or expired goods. Okay, so that task we've identified as potential. Okay. The cost of a baker to their employer is about $48,000 per year on average, according to the census. So the value of automation for a small bakery, if it's, say, one that has 5 bakers, would be 48,000 times the 6% of their job times the 5 bakers is $14,000 per year. And that is much less than the cost of deploying a computer vision system to automate this. The benefits are much less than the costs. This bakery would not want to automate this. Okay, and that's really the heart of our analysis is going to say there are lots of things, right? We see this today in society. There are lots of things that you can imagine automating with the existing technology we have that we choose not to because it doesn't make sense from a cost basis. And that's also going to be true for AI. Okay, so if we think about then this analysis framework that people have been using, we can then make clear what our extension is going to be. So again, if we talk about this AI exposure version of it, we're going to take this list of tasks done by workers in the economy from the ONET database. We're going to classify each task according to the similarity with AI capabilities, right? And in the last example, we talked through this just informally, but in fact, what people have typically done is they might ask machine learning experts, or they might use patent language similarity or some such measure. And that's going to give you a list of tasks at risk of automation. And what we're going to say is, wait, we want to add some additional steps here. We want a more end-to-end analysis. And so what we're going to do is first is we're going to say, well, rather than talking to, for example, machine learning experts, we're actually going to survey task experts about it. And we're not going to ask them about computer vision specifically, right? Because your average plumber doesn't know about how good an AI system is. What we're going to ask them is, what's the performance required for a particular task? Do you need to be 90% accurate, 99% accurate? 70% accurate is good enough, right? So we're going to get some distribution of how accurate you need to be to actually do this task effectively. Then we're going to say, okay, let's estimate the cost of building an AI system that has that level of performance, right? And this is going to be a little bit of the secret sauce that we're going to bring in here, right? And I'll tell you sort of why we think we are able to do this well. But once you've estimated the cost of building a system at that level of performance, then you can make the direct comparison, because you can say, well, there are a certain number of humans doing that, and here's how much it would cost to build an AI system. Do you want to replace them? And so that's our last step here. And we estimate where the benefits will outweigh the cost. And that gives us our list of the tasks that are at risk of automation. And as you can imagine, this additional condition is going to bring down that share of jobs that you might think that are at risk. Okay, so I just mentioned, it's this middle step here, right, that is really the one where you'd say, okay, how do you know how to predict the cost of such a system, right? That feels like there could be lots of variations. How would you get at this? And it turns out that in AI, there's this very robust and important pattern that all of the big AI companies are following when they think about building their capabilities. And that relates to something that are called AI scaling laws. So this is the most technical computer science technical graph I'm going to show you, but I think it's a really, really important one. So let me break down what's going on here. So this is, by the way, from a paper in 2020 by Hennigan. So let's focus for the moment on the top left-hand image, left-hand graph that focuses on image. So this is image recognition, the problem of you show a computer a particular image and you're trying to see how well it does. And on the x-axis here, we're going to have the amount of compute that is being used. These are in petaflop days. If you don't know what that means, don't worry about it. Just think about it being quite a big unit. And notice that we're in factors of 100 on our scale. So it's logarithmic, and these are big jumps. So this would mean if you move from here to here, that would indicate you're using 100 times more computing power in order to do that analysis. And then on the y-axis of all of these things, we have the loss, which is, sort of a measure of how far off you are in terms of what you're trying to achieve. For the sake of this, you just think of this as like the errors that you're making, right? So on this task of image recognition, it's how often do I show you a picture of a cat and you're like, this is a dog. And so you just get it wrong. And notice that's also on a logarithmic scale. So the reason these are called power laws is that they follow these polynomial power laws. Okay, so that's the graph. Then each of these traces that we see on this graph represents the training of a particular model. And the color of that model corresponds to the number of parameters that it has. So for this green line, we can think of this being a model that has 10 million parameters. And what you can see is as you start to train this model, the errors that it makes goes down. That's good, right? We're training it with more and more data, more and more compute, and it's getting better and better and better. And then it hits this point, and then the slope changes a lot, and it sort of curves off and becomes less effective. Now, we could have used a smaller model, say in the blue, and we would have seen it would also have dropped in terms of the errors, but it plateaus earlier. And so what you can see is collectively, all of these different lines trace out this dotted line. And that dotted line is the power law. And what it says is, if you tell me the amount of error that you want to make on a particular problem. So you say, well, I only want to make 5% errors on my computer vision system. You can find the corresponding loss and you can go over to it and you can say, okay, this is what I want. It's going to take me this amount of compute. And the best model for me to use is a model that has a certain number of parameters. And so this is actually giving us a recipe for a given level of performance, how much compute, how much data, and how many parameters the model actually needs to have in order to do it. Okay, and it turns out that these power laws are incredibly pervasive in deep learning and AI and the AI revolution that it has created. And it means that you have this very clear recipe that comes to it. And so if we think now about all 6 of these, you can think about, well, what if I wanted to have the amount of loss that I have for a particular problem? You say, okay, great. Well, if you convert these equations to what they actually mean, it says that for these particular images, which is a pretty small image, 8 by 8, if you want to have the amount of loss you have, you need to use 40 times more compute. And of course, if you wanted to have the loss again, you'd need another 40 times compute. Notice that for example, video on the far right-hand side here, it takes more compute in order to improve performance, right? If you're doing math, similarly, about 140x. And very relevant for what's going to come later, when we think about extending these kind of analyses to large language models, in language, it takes a huge amount more compute in order to do it. Every time you want to have the loss, the errors that you're making in language, you have to increase the amount of compute you're using by a factor of almost 2 million, right? So these are very, very large numbers. Okay, so AI scaling laws, as I said, very, very important and very central to how computer scientists, and in particular, how these big AI companies think about it. And so this is very directly, for example, what OpenAI thinks about when they think about investing in GPT-5 and what level of performance it will get. Okay, now all the graphs I've shown you here are really about specifically training a model from scratch. In fact, for most users today, they're not going to do that. They're going to use foundation models. But it turns out that there are actually power laws for that as well. And so let me just sort of talk about what the process looks like so that you have a good sense of it. Okay, so again, let's think about, we're doing image recognition. We have someone has trained a database on ImageNet, one of the most famous data sets here, created by Fei-Fei Li at Stanford. And that's got 1,000 different categories of things: cats, dogs, etc. Now, the problem is there are lots of real-world scenarios that are not well reflected by this database. And so we did a number of case studies for our analysis, and one of the ones was a company that actually looks at drilling equipment. Okay, and so what happens is they sell to a bunch of drillers, and when those drillers break something, right, they take a picture of the thing that broke, and they send it to them by email and say, send me a new one of these ones, right? And you can see, like, the actual state of these things is, they're all covered with mud, and, it's going to be some part, call it, R22, right? And part R22 is not in the ImageNet database. And so if you use a system trained on the ImageNet database, it's going to, you show it in R22 and it's going to be like dinner plate. And you say, no, that's not right. It's a specific thing. So you have to do this fine tuning that says, okay, the system has a lot of the architecture I need to recognize edges or colors or things like that, but I need to train at least the top part of it in order to recognize the things I care about. And that process is fine tuning. And so the important thing here is that the labels just don't even exist before that. Okay. So as I mentioned, the nice thing here is that there are scaling laws that also apply to fine tuning. And so in the same way that we had a recipe for how to train a model from scratch, we also have a recipe for how to do fine tuning on these models. Okay, great. So that we now have this recipe, we can now think about this as part of the overall cost analysis that we want to do for AI. And you can think about that as falling into the following categories. So there are a bunch of fixed costs, engineering costs for implementing and maintaining these systems. There are performance-dependent costs. So there's some initial training costs of actually doing it, right? These could be fine-tuning costs. And that comes both in terms of the compute that you actually have to use and the data, because data often comes with a cost. You also often have to retrain the models as well, because they become out of date. So for example, we did a case study with the supermarket, and they had to update this about every week or two, because if they didn't do that, new products were on the shelves and they weren't able to predict them with the model they had. And then you have scale dependent costs, right? Which is saying about the actual running cost of doing the inference on these particular things. Okay, so the scaling laws give us some pieces of this cost analysis. We estimate the rest of them with pretty extensive work that we had done. So we did 35 case studies. We wrote a teaching note on this. We did some analysis of the AI literature. And in fact, for some of the scaling laws needed here, we actually wrote an AI paper deriving them because they didn't exist in the literature. So all of those are then going to give us this way to say, if you have some initial model, right? So this is a pre-trained model or foundation model, they're sometimes called, right? That has some level of performance. So, it's 93% accurate or something like that. And you say, okay, when I move it to this new domain, right? It was trained on dogs and cats. I move it now to these drilling well parts. The first thing that's going to happen is performance is going to fall. And it turns out that we can sort of predict how much it's going to fall, in part because of the entropy. And then we can say, well, there's a certain amount of accuracy needed. And so we're going to do this fine-tuning process to get to the accuracy we need. Okay, and this is, as mentioned, this is what we derived in our 2024 AAAI paper. Okay, so that's the AI side of things. Now let's think about cost effectiveness of the tasks themselves. Okay, now hopefully you can sort of immediately see that even though AI is all very fancy and all of that, a lot of the standard economics of thinking about investing in automation are going to apply here as well. In particular, what you're going to have is a minimum viable scale. And so what I mean by that is, if you think about humans doing it, right, hiring a human for an incremental hour, right, is very steady, right? If you have 10 or you have 20 of them, the marginal cost is not going to change very much. But for the AI system, the average cost initially is going to be very high because you have to pay that big cost up front for that training, right? And just to put this in context, right, like the real cutting edge models here now can easily cost 100 million, and they're well on their way to the $1 billion mark to train such a thing. Smaller systems cost much less, but still would be pretty expensive, right? And so you have an initial cost that's quite high, but of course, as you amortize that over a larger scale of deployment, you get those average costs fall, and there's going to be this thresholding point where you'd say that's where the machine has an advantage over the human. That's the point where you actually do want to apply it. Okay, so let me give you an example of this that really comes from our data. So if you think about a supermarket, and one of the tasks that a retail supervisor does is they go around and they look and they say, are products on the shelves? Like, is it, is something empty? And separately, is the price that is listed the correct price for the product that is shown? Now, when we do the economics of this, what we find is that if you are somebody big like Walmart, the answer is absolutely you want to do this. And in fact, Walmart is already doing this. They are already putting cameras in the ceilings of their stores in order to be able to do this in an automated way. And that makes sense. They have that minimum viable scale easily. At the same time, we also see that for a small corner store or something like that, it absolutely doesn't make sense to do this, right? The cost of putting that in would not be worth the amount of labor it saves for the person running the shop in order to actually do this. And so we can start to see now that there's one of the dimensions of our analysis is going to say that if you are in a small enough business, that business is not going to want to automate on its own, right? And so I already mentioned earlier, we're going to later talk about AI platforms. And so we'll think about, well, could you spread those development costs and stuff? But for the first piece of the analysis, we're just focusing on does the firm itself want to do it? And the answer is if you're a small enough firm, you often don't want to do it. Okay, so with that recipe in mind, you can see that, as I just talked about on the last slide, if you don't have enough scale, you're not going to be attractive to automate. The other thing that we see is the really dominant force is that if you need a very, very high level of performance, that also can be very restrictive. And so another specific example from our data, think about if you're a nurse anesthetist, right? So this is the people who monitor you when you're under anesthesia. And one of the things they have to do is a visual task. So they have to look at your face, look at your pupils, look at the color on your face, and decide, are you in distress while you're in surgery? So that's one where you have to be incredibly accurate. And so, because of that, the cost, remember with these power laws, every time you want to have the error, you have to pay this cost, this additional multiplicative cost. That means that you very quickly get to very high costs. And so many of these very high systems, you would need an enormous scale in order to make it attractive. All right, so that gets us then to the fun thing. So let's compare our result to what we saw before for the analyses that focused only on AI exposure. So let's start here with just the number of jobs in the whole economy. So again, we're thinking of exposure to computer vision. And we see that if you just do AI exposure analyses, then you can say, well, what share of jobs in US businesses could have at least one task that could be automated? And you would conclude, oh, well, it should be about like 35, 36%. Okay, quite broad. But if you add that restriction, well, it has to be cost effective, right? The company actually has to want to replace you and not have that be a more expensive, costly option. Well, now that actually falls down to about 7 or 8%. Much, much less. Okay, but that's just one task. I mean, maybe more relevant is the share of the wages that are actually being paid for that. And there you get something similar. So about 1.6% of tasks in the US economy are sort of vision-related tasks. And therefore, in theory, could be replaced by an AI vision system. In practice, we see that only about 23% of them are actually attractive to do. Okay. Now, these estimates, right? I mean, I showed you that cost diagram earlier, and you might say, well, wait a minute. There are lots of assumptions that have to go in there, and that's absolutely true, right? Even though we have this very nice recipe, right? There are a bunch of things about the cost of the workers that are going to do it and so on. You might say, well, how much confidence should I have in those? And the answer is like they come from real data, but we would definitely want to check some robustness. And so that's what we do. And so let me start on the cost side of things, right? So what you can do is you can say, well, what if cloud pricing was much higher than the base case? So the base case is going to be represented by this number. And here you see on the x-axis, again, we have the share of the vision tasks that are attractive to automate. And you can see that actually changing the cloud pricing, even by a factor of 10, which is what this analysis is, does not actually change the percentage very much. And that's just because these scaling laws mean that you just need a lot more computing power and data and stuff in order to do it. If you change the entropy of what you're doing, which is like, think about it as like how complex the problem is, if we got that a little bit wrong, okay, that will change things a little bit, but not hugely, differences between about 20% and 24%. You can change how long, when you build a system, how long it will last. That changes, obviously, the investment side of it. You can train how often you have to retrain it. Those change it a little bit. Something that can change it a fair bit is accuracy, right? So if the systems need to be much more accurate than we're predicting from these folks, then that would actually significantly decrease the amount of automation that could happen. We can look at data costs. That matters a fair bit too, and engineering costs matters a fair bit. But notice we're still within this range of about 18% to 33%, right? And so we're still very, very far off the AI exposure numbers, which are much, much higher. All right, so that was some cost robustness. What about robustness to the benefits that are being provided? Because right now our assumption is that we're replacing the human, right? So we get to save their labor and the wages that we would pay them. But in fact, maybe when you replace it with an AI system, you say, well, now I can run 3 shifts on my factory rather than just 1 shift, right? And so maybe we're understating the benefits that would come, or possibly overstating them as well, right? And so here what we've done is we said, well, the base case is the wages are getting replaced, right? And we can say, well, what if the benefits were only half as much as we were predicting? Well, now the share that you'd want to automate goes down to about 18%. And if the benefits were twice as big, they would go up to about 30%. All right. So we do see this, but notice you need very, very large numbers, like 8x change in the benefits to get up to, for example, in this case, 43, 44%. Okay. So this hopefully gives you a lot of confidence that actually a lot of these numbers can change and you still end up in a pretty similar range in terms of your predictions of the share of these AI exposure tasks, which are much, much higher, that actually are cost effective to automate, and therefore telling us that there's not as much automation that's likely to happen in the short run as you might expect from those other analyses. Now, one of the things you might say is, well, okay, you've done all this, but is this measure good at predicting actual unemployment shifts that have happened? And so what's nice is that there's some work by Frank et al. That has actually done this. And so all of the non-bolded stuff are the analysis they've done, and then the bolded part is going to be our extension of that. So what they did is they said, if we think about a whole bunch of other measures that have been created about routineness, for example, by David Otter, who we mentioned earlier, there's some of the stuff by Webb et al. Looking at robot exposure and things like that. And you can see that all of these do significantly predict the unemployment risk. So that's what we're looking at here is unemployment risk by state, month, and occupation over the 2010 to 2020 period. But it's predicting a pretty small share of the R squared, about 2-3%. Some of these up to about 10%. And then the bolded here is our measure. So this says, okay, well, does our specific prediction that is not just about do you have exposure, but is a cost effectiveness, does that predict it? And the answer is it does. And actually, we can explain even more of the R squared of unemployment risk than can all of these other measures, right? Now, you might say, well, that seems a little odd because you're only looking at computer vision, whereas they're looking more broadly, right? I think what's going on there is that the same things that make tasks attractive to automate in computer vision also make them attractive to automate with a large language model and stuff, because the economics of these models is quite similar, right? And so I think what we're actually doing is predicting actually where these systems are attractive to deploy. Okay, so hopefully at this point you're feeling pretty good because we have this estimate. It's quite robust to a bunch of changes, and we see that it is actually very predictive in the real world of the thing we care about. Let's now, though, say, well, we might want to extend this to think about actually how AI can spread and the job replacement that would imply. Because so far we've just looked at a one time period and asked about that one in particular. And so we're going to focus particularly on two things that would make deployments more attractive. So the first is if you get AI as a platform, right? We've been analyzing the economics of this at the firm level, but we can get larger scale by deploying across firms. And so we can think about that process. And then we can also think about a sustained reduction in development costs. Okay. So if we focus first on the first one, the AI as a platform, we can think about the useful scope of a computer vision system. So if I design a system, let's think again about the bakery example, how broadly can it be used? So, we gave this example of bakeries before. Surely if you are a big bakery like Hostess, right, it is actually attractive to build a lot of these systems. And so in fact, historically, in many production facilities, you have some computer vision systems. They're older computer vision systems, but they are already doing this kind of thing. But then you can ask your question, well, if Hostess trains a model to do what they care about and to make sure that they can predict well, how well is that going to do if you try and apply it to across all of the industry group that they're part of? So can all bakeries and all tortilla manufacturers use it? Right? You might say no, in which case you'd sort of be limited in the way that the AI platform could be built there. But if it could be used, that would give you a lot bigger scope for deployment. And you might say, well, maybe I could use it for all food manufacturing, right? Or all tasks related to food quality across the whole US economy. So if you make that change, you see that so here again, we're looking at the share of wages that are exposed to computer vision. And you can see that at the individual business level, that's our number from before of 23% of the vision tasks are attractive to automate. You can see that if a single system that you're building allows you to do things across the whole industry group, now you jump up to a much higher number, right? And so, as you can imagine, there are not a lot of other food quality things outside of it. So you get a little bit more as you expand out, but not too much more. So what is this telling us? It's telling us, first of all, that most firms lack the scale to automate tasks. That's really, you can see that here, that the AI platform has more scale. And that suggests to us that a big thing that people are going to do is build AI platforms. These platforms do have the scale, but even at the level of the platform, there are some tasks that it's just too expensive to do. And even if you had all of the tasks in the whole economy working on that, you would still not want to build an AI system for that. Humans would still be the more attractive option for those tasks. Okay, so this might make you think, well, gosh, if AI platforms are going to come in and they're going to be much bigger, that could happen very quickly. I think we will get some platforms that will come in, but how quickly, I think, is important to question. Because if you think about automation in that process, it can often be very slow. So I think a nice example here is self-checkout systems, right? So in the US, self-checkout systems are growing by 11% per year, which is pretty fast at the level of market growth for that particular thing, but this is too slow to really change the overall dynamics of what we were just talking about. Okay, and so I think what this is telling us is, like, we expect a bunch of tasks to be attractive at the level of an individual firm, and then another set of tasks to be attractive to do in the form of an AI platform, and that will be created, but it's going to take a while for that to spread out, and so that's not going to immediately cause a lot of labor disruption going in. Okay, now I think an even more promising area of change that could affect actually the attractiveness of deploying these systems is a cost change. And so let me give you just one particular example. This is from a paper from folks in my lab and folks from Epoch. And what it's doing is this case is in terms of large language models, although we've also done it in terms of computer vision systems. And what it's saying is, if you think about a particular model at a time, so a language model there's one called Megatron or GPT-2 people may be aware of, or Gopher, and you say, well, in later periods, how much compute does it take to get to that same level of performance, right? And you can see that a few years later, you're down at maybe 40 or 50%. A number of years later, you're down at like 20%. So this is saying that New models, because they have some algorithmic improvement that has gone on that makes them more efficient, they're able to do the same task with less compute. And that could imply a bunch of savings, right? And in fact, this is happening very, very quickly. So we see that on average, compute needed falls, it halves every 8 months. So that's quite quick. But we also shouldn't be overgeneralizing about this particular pace, this incredibly rapid pace of improvement, because AI costs have this almost cost disease problem, which is that if you have cost of your data and cost of your compute and cost of the humans that are involved, right? If one of those falls very quickly, the other ones quickly become the bottleneck, and that becomes the restriction on deploying it more broadly. So even if you get, the cost of compute going down very low, you would still say, oh, the other cost will be restrictive. Okay, so we can actually think about this very specifically in terms of how fast it falls. So again, this graph, we're going to have the wages that are exposed to computer vision, and then the values that we're using from the Census Bureau from 2022. So that's the 23% we've been talking about. And this says, well, if every year costs decrease by 10%, we're going to follow this red line, right? It is the case that some things will become more attractive, but you can see it happens fairly slowly. And so even in a sort of 2-decade time period, you would only be up to about 35%. You can say, okay, well, what if it's 20% improvement per year? It is indeed faster, but you can see it still takes quite a while. And you need something very dramatic, like a 50% cost decrease over time to get this to happen a lot more quickly. While we might expect that in some areas in terms of the algorithmic progress, in terms of the cost of humans deploying these systems and stuff, I don't think it's improving that fast. And so I think we're more likely to be on one of these other curves. Okay, so given this, we could ask the question, well, if we think about the normal replacement rate of jobs in the US economy, how much would these kind of cost decreases change the churn in the economy? And the answer is, after that initial switch, after that first 23%, which is a big jump, right? Then we'd see, okay, well, if we have a 20% decrease, that would represent about 2% change in the workers in the economy. That's versus an 11% number, which is the average for private sector job destruction over 2017 to 2019. So you can see that, yes, it would increase the churn in the economy, but it's not. We wouldn't expect it to be just a dramatic change that is going in. Okay, so I'm coming to the end of my time here. Let me just say a few words about how this framework applies more generally to large language models. So the first thing to say is, I think this path that we have on how to do this analysis is very generalizable. I think we can use it directly with large language models. And in fact, we are in the process of doing that exact thing. And so stay tuned in another 6 or so months, and we'll actually have a version of this for large language models. It is worth saying, we're in large language models, there's this question about, well, will these ever larger large language models enable us to do things without all this fine-tuning and stuff? Maybe we can just use it off the shelf, right? And indeed, we of course see that with ChatGPT going to GPT-4. The plan is to go to GPT-5. We can imagine this mattering. And if that's true, what it would do is it would bring down the cost of the fine-tuning that's involved in this. And so what we do to test this is we actually think in our analysis about a bare bones scenario. So we say, let's imagine data was free and compute was free, and there was minimal engineering effort required. So you don't have to have really fancy people doing fine-tuning, but you still need a bunch of people who understand how to put the system together and the like. Well, under those conditions, you do get a jump up from about 23% to about 50%, but you still have a lot of jobs that are not attractive to automate at the firm level. And that's just because, even when you do that, you'd say, lots of jobs, they're just done by very few people in some part of a business, right? And lots of stuff that you say could be automated, you just choose not to, right? And so if we think back to that automation example of self-checkout, right? Lots and lots of stores still don't do self-checkout because if you only have one person and they're standing there, it doesn't make a lot of sense to build an expensive system to replace them. Okay. And I think another good analogy that you can think of here is electronic health records, right? We all know electronic health records have big benefits, but when you actually look at deployment, you see that it's really focused in very large businesses that have scale economies and not in very small ones that don't have. All right, so let me wrap up here. What we see is that the number of jobs that are cost effective for firms to automate is much smaller than is implied by the works that have been focused on AI exposure. And this arises because there's a long tail of systems that are expensive to build and that there's not enough scale in order to replace them. We see that this measure that we created is a good predictor, in fact, a better predictor than other measures have been, of actual unemployment risk that is happening in the US economy. And what we expect is initially a jump in automation, right? That 23%, that's a substantial change the economy is going to go through, but then further adoption will require industry level platforms to gain scale, deployment costs to fall. That will take time. And that means that we should expect there to be initial period of a lot of flurry, but then more continuity. And that will give us some policy time to actually respond to this. And then lastly, we think that large language model effects will also be limited by development costs, albeit perhaps less because they might be able to scale over a little bit greater stuff. And with that, I'll stop. Thank you very much.
Great. Thank you so much, Dr. Thompson, for that excellent presentation. Like even recently, I've seen some articles that still quote Carl Frey and Michael Osborne's paper from a decade ago that made headlines saying, 47% of jobs will be replaced by AI, because again, they were looking at just AI exposure, jobs with AI exposure. So this is great to have this advance, a better model incorporating some other elements. So maybe I could start by asking a question that was just in our chat, as well as adding kind of a portion of my own question, which is in the chat group, people were asking about, the cost of these systems. I think there was a thought that these costs will actually get very low, right, as these platforms get deployed. So I think that's number one. I think on my end, since I work in the business world too, it seems to me that in the business world, at least, it's not just a matter of the cost of the singular system. It's two issues. One is a lot of last mile problems that need to get worked out, right? Something like alignment or explainability, and some other last mile problems with just how these systems work. The second is making these systems more holistic rather than narrow. So for example, a baker does many things, right? In a small bakery, other than check the quality, right? Now imagine a few years from now, that may be enough time to work out some of the last mile problems, and that may be time to work out some of the holistic problems. Like now we could have an AI system that several companies might work together on, and it can do customer service, it can take payments, and it can also check, the good of the product, right? So anyway, I think that's one, that's the major question we're asking, which is, potentially can these things happen much faster? Maybe not in the immediate short-term future, but at least in the medium term.
Great. Okay, so let me pick up a few different threads here. So I mean, I definitely agree that the cost of these systems is going to fall, right? But think about that graph I showed where we said the 20% cost decrease. That's 20% per year, right? And so, that would be a very dramatic cost decrease, right? Like you would very quickly, the prices would fall. And what we still see is even under those scenarios, it still takes quite a while to do that. And that's just because, the sort of the range of costs of these systems, you need an exponential cost decrease in order to get a linear change in the percentage of tasks that you want to automate, right? And so like I absolutely agree costs are going to fall dramatically. And also it's going to you really need, you need orders of magnitude of change in order to really change this number very quickly. And so I think we will see that, but I still think that's why we still end up with a system that says it takes a long time for these to roll out. To your two other points, I agree completely. So this last mile problem, I think, is a really big challenge, right? And I think it comes in because, if you have to fine tune on your particular example, then you have to do that requires a whole bunch of infrastructure and stuff to actually to do it. There are also just last mile problems of someone has to install it in the roof of the bakery and maintain that system, and like you change your product mix and all of a sudden you have the wrong labels and stuff like that, right? There's a bunch of stuff you need to do in order to do that. And I think that's, that's why when you see that bare bones analysis, even just a minimal engineering effort is enough to make lots of systems unattractive because of that last mile problem, because it does matter a lot. And then finally, you brought up something which I think is a very good critique of our work, and basically all of the work that looks at task-based automation, right? Which is like, if you think about what Frey and all were doing, right? They're thinking about it at the whole level of the whole occupation and saying, well, is anything you're doing, at risk? I think the field as a whole has moved forward a lot by looking at individual tasks, right? But in getting to the level of an individual task, we've broken apart away from processes. Right. And this question of like, well, do you even want, like, do you want to automate this part if this other part, depends on that first one and this part can't be automated, for example. And so that's some work that we're actually trying to follow up on now. As you can imagine, that's actually a lot harder. Seeing those dependencies and having some sense of how they relate to each other is a very hard problem.
Great. Okay.
Can I ask a question?
I have
Randy.
a question. Hi, can you hear
You
me?
first.
Hi, hi, Neil. Great presentation. This is Lian from University of Toronto. So I learned a lot from your presentation. I have one question, kind of regarding income equality. Do you think that what would be your conjecture or speculation on the effect of AI on kind of income equality? So maybe they can crowd out some people's job, but also some people can pick up, can use the AI kind of more efficiently. That might widen the income inequality. On the other hand, so if people can use AI more equally, it might reduce the income inequality. So I think this is also a very important topic to think about how AI affect people, the kind of income inequality. Now people focus more on kind of a growth side, or the kind of job replacement. People completely disappear to lose their job. So I think maybe another kind of very important dimension, sort of also very important, is about the income inequality. So overall.
Yeah, great question. So let me give you a first answer and then point out two important limitations to it. So when we analyze the mix of jobs that are attractive to automate, what we find is that it's actually much more even in terms of the education level than other analyses have done. So a lot of other analyses have said, oh, this might be disproportionately automating like white collar work, right? And others have said, no, the sort of historical automation literature said it's blue collar and routine tasks in particular that are getting automated. We find that at least with computer vision, it's pretty flat. And so I think at that first pass level of people losing their job and that creating inequality, I think, it doesn't look from our analysis like this is going to be a big push in one direction or the other. Now, the two caveats I want to put on that analysis are, the first one is to say that isn't a general equilibrium result. That's a partial equilibrium result, right? And if you think about actually, some mix of companies becoming larger or things like that, we could have larger effects. And we're actually doing some macroeconomic work right now, trying to estimate what that would look like. But we don't have an answer to that yet. The second thing that I think is important here is that, as I mentioned, we're focusing in this paper specifically on replacement. And I think a lot of the income inequality effects or disparity effects are going to come in based on augmentation, right? Because we've seen in a bunch of recent studies that like call center worker automation disproportionately benefits the bottom folks, right? Now that's not, I don't want to say I strongly suspect that initially it benefits the bottom people, and then over time those bottom people get replaced, right? And so I don't want to assume that is necessarily good for them, but I think in order to get a good answer to your question about inequality, we need to think about both replacement and augmentation, and we're also doing some work on that, although don't have it yet.
Great. I think next up is Professor Longchen.
Yes. Hi, Neil. This is Longchen from Luohan Academy. Okay, so
good to see you.
Firstly, I really like I really liked the paper. So I think it explains a lot of things to me. Actually, Mike Spence and I talked multiple times about this, and he was really worried that AI will replace the labor, especially for the developing countries. So that, I mean, there's a lot of questions like that. And another type of confusion is that people have been advocating for digitization for a long time in the Western world as well as in China. And in China, I've watched, I think it's very interestingly that many companies, including Alibaba, is helping companies to digitize their business, but it's hard for them to explain what's the value of this because it's not clear. So there's many companies that adopt, for example, cloud computing and the digitization of some of the business procedures. Then they just then they kind of reduce this to the CTOs, but they don't know how much they should spend on it. Stuff like that. So I think this is crucial. Here you point it explains a lot of things. I think it's really from the business practice point of view to look at the adoption of the technology, and it's not just like science projects. So I think it explains a lot of things to me, especially, for example, it says that because it's really just, you can only replace part of the procedure, right? And so that explains for most of the firms, actually, they will adopt some of the stuff. So that becomes the efficiency improving rather than disrupting. So that's exactly what we observe nowadays. I see almost no company nowadays being disrupted by AI. They use this to improve their efficiency. It's not really replacing labors. And also, it has many more predictions. For example, it predicts that larger firms will benefit a lot more because the scale, But of course, the smaller firms, because they have the new ones, they start without the burden, the implicit cost of adopting, so they are native, more native. That also explains the small firms' advantage. And also applying the same logic, there's many jobs. Information value is only a small portion or some portion of the whole process. Many jobs involves the physical labor, some judgment, this or that. So it's really just part of this, and that really explains that most of the firms are not disrupted today. Even we've been talking about digitization for a long time, and so I think that also explains in general that. In fact, I think this story implies to almost all the technological revolutions in the past 200 some years. We've never seen unemployment rate going up because most of the time only replace a portion of the work. And I think, and the speed is the key, but you have the time to adopt. Some adopt faster, some slower, but human work in practice, in business, is a complicated process. It's just very hard to explain this as wholesome. So I really like this, and I think it helped me to learn a bunch. My only suggestion for you is that you described it more like, even though I think it's intuition rich, but really motivation wise, and also talk about its implications is it's too narrow. I think it has many predictions you can kind of lay out to many business phenomena. It helps firms to explain how much they should spend, stuff like that. Predicts the speed of the change of the industries. I think it has many implications. I really enjoy it. Thank you.
Well, thank you. And that request to write more about the implications of it is always very welcome. And it's I think our hope is that we're going to write sort of a series of papers to bring out some of these things, because as you can imagine, we're a little space constrained. I do want to say, I think that something you said there is just really important, right? I mean, there's a very clear prediction, which is that this is going to happen predominantly in large firms, right? And I think that's exactly what we see, right? If you think of the census work that is done by Christina McElhern and others, right, you see that it is the very big companies are doing it a lot, and the very small companies are not doing it very much. I think that's very much in line with what we see in our analysis. The last thing I would say is you mentioned this sort of distinction between the developing world and the developed world here. And I think what's nice about this framework is it also allows you to say, like, you can think of these different cost things, and you can say, well, okay, in China, the cost of labor is different, right? And the scale of the labor replacement is different, but so is the cost, and so is the cost of the engineering labor and stuff involved, right? And you could do those, and you could ask yourself the question, like, is that enough of a change to make much of a difference in the predictions of what will be automated and what won't be automated? But it's, there's a very clear, like, you don't have to replace everything. You only have to replace a few of these costs to see what effect it would have on other countries. And I think that's a pretty nice feature of the framework itself.
Yeah, I think my last sentence, I think a key intuition here is that most of the time when we talk about this kind of disruptions, actually, most of the time it show up as efficiency improvements for companies. And also, the so-called disruption is really they find certain products that is so scalable. It's really just solve one small problem, but it has very scalable applications, and that is a disruption we're talking about. But for most firms, it's not replacing this whole firm. I think that's a general phenomenon.
Okay, great. So Neil, I know we're a little over. Would you mind going on till like 10:10?
So unfortunately, I do have someone already waiting for me, unfortunately.
Sure. Okay, in that case, any questions we'll collect, and maybe I'll email you them and we can take that offline.
That would be great. My apologies, Sam and Angelique. Wonderful. Thank you, everyone. Wonderful talking to you today.
Yeah.
It was so great to have you. Thank you, everyone, for joining.